Welcome to a brief discussion on carbocation rearrangements. I'm Professor Davis from the Chem Survival YouTube channel and chemsurvival.com. We're going to start by thinking about first-order reactions, those nucleophilic substitutions and eliminations that you've no doubt heard about in class. And you know that what these two reactions have in common is that they both proceed through a carbocation intermediate, which is metastable. This means that the carbocation intermediate will exist for a certain period of time. Now, when weak nucleophiles and bases are in play, like they are in the first-order reactions we're talking about here, sometimes they're a little bit slow to either go through a nucleophilic attack or to abstract a proton and act as a base. And in the intervening time, the carbocations have an opportunity to do something. They can rearrange to become a more stable carbocation. So if there is a way during the time that they are alive that they can rearrange to a more stable configuration, they will. And that means that the electrophilic site on the carbocation can change. So given enough time, we're going to get a rearrangement that will give us a more stable carbocation. So let's talk a little bit about carbocation stability so that we get a good reminder of what drives that. Okay, so now that we know that carbocations can rearrange, let's think a little more about why. Remember that carbocations will only rearrange when there is an energetic benefit to doing so. So let's think about what type of changes will add extra stability to carbocations in similar species. There are really two different things I'm going to talk about during this talk, and you can probably think of a few more that might affect it as well, but I'm going to stick to the big ones here. The first one is the substitution level. Remember from our previous talk that methyl is a very unstable carbocation, while primary carbocations are only slightly more stable, and secondary and tertiary carbocations are what we tend to see forming most commonly in first-order reactions, with tertiary being the best. Now also, if you go back and take a look at our ring strain talk on our YouTube channel, you'll see that rings are most stable when they have 5 or 6 carbon atoms. So cyclopropyl and cyclobutyl configurations contain a great deal of ring strain, and if they can relieve it by rearranging to become cyclopentyl or even cyclohexyl groups, they'll do that. So that energetic benefit is there. So as we've drawn these different species here, stability increases as we move to the right. So we expect carbocation rearrangements to always include a certain change that takes us farther to the right on this diagram. Okay, so let's go over a few general rules here about carbocation rearrangements. The first rule is that carbocations always shift to increase their substitution. If they don't relieve some kind of strain or get some kind of energetic benefit, they're not going to rearrange. So again, we're looking for situations where the shift can increase the substitution. The other instance in which these kinds of rearrangements occur is to expand small rings, like cyclopropyl and cyclobutyl rings. And another rule to keep in mind here is that the energy required for a hydride shift is less than that required for a methyl or alkyl shift. So hydride shifts will occur before an alkyl shift. If there's a possibility for both, we always go with hydrogen. Okay, so let's take a look at our first example of a carbocation rearrangement, one known as a hydride shift. So here I've drawn for you a secondary carbocation, but not just any secondary carbocation, one in which there is an adjacent tertiary carbon. So here's our secondary carbocation center, but right next door there's a carbon that's more substituted. So what can this carbocation do given sufficient time to increase its stability? Well, let's draw a copy over here and watch what happens. A hydride shift is going to take place, and by hydride I mean not only the hydrogen atom, but also its bonding electrons. So as the hydrogen and its bonding electrons both move over to the carbocation center, let's watch what happens to the charge. As you can see, the charge has relocated to the tertiary carbon. So I've created a more stable carbocation via this hydride shift. So given sufficient time, I would expect the tertiary carbocation to be the intermediate which I would use to predict the major product. In a skeletal structure, it would look something like this. Here's our secondary carbocation, and of course, since the hydrogen isn't shown, we'll have to put it in there in gray. It shifts and ultimately just relocates the positive charge to a more stable location. Now let's take a look at secondary alkyl shifts. Here's a secondary carbocation, but this time my secondary carbocation is adjacent to a quaternary carbon, that is, one which is only bonded to other alkyl groups. So a hydride shift is no longer possible. What is possible, however, is that instead of shifting a hydride, I can shift the entire methyl group, or to be more accurate, a methide group, including its bonding electrons. And when I do this, notice again the charge moves to a more substituted position, creating a tertiary carbocation. In terms of skeletal structures, a carbocation which is primed for an alkyl shift would look something like this. And when that shift takes place, an entire alkyl group is going to move. So now not only have I relocated the charge, but I've also changed the substitution of what was once the carbocation. So it's a little bit more complex, but again, given sufficient time as an intermediate, I would expect the tertiary carbocation to direct the major product which forms. Just as one last example of a carbocation rearrangement, here's a cyclobutane ring. Now in this case, the cyclobutane ring is adjacent to a secondary carbocation. And when we have a secondary carbocation next to a strained ring carbon, something very similar to an alkyl shift can occur. In truth, it really is an alkyl shift. It's just that, in this case, it's tied to a ring. So when an alkyl shift takes place here, the ring is going to expand by one carbon. Let's watch this happen. So as you can see, I have not really changed the overall substitution here. I've gone from a secondary to a secondary. But what's driving this forward is the energetic benefit of ring expansion from a 4-membered ring to a 5-membered ring. So again, given sufficient time as an intermediate, I would expect this carbocation to rearrange to the cyclopentane version. And that's what's going to dictate product. So here's my original carbocation, and here is the ultimate result of my carbocation shift.